Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey Houston, we don't have a problem. Today what we want to do is we want to talk about the kinetic molecular theory. Now theory, right? Theory. So the word kinetic, what does the word kinetic mean? The word kinetic means like the art of moving, right? So, or motion. So you could say, for example, that Michael Jordan is kinesthetically gifted, right? He's good at moving his body. And then the word molecular comes, of course, from the word molecule. So it's like the moving molecule theory, kinetic molecular theory. So it's an idea that, well, here's the big tenet, is that all molecules are moving. That's right, all molecules are moving. Jot that down. And you're probably aware, the idea that there's this thing called kinetic energy. All right, so energy is what? Energy is the energy of motion. As something is moving, it contains energy. So if it strikes me, then, well, I've felt that energy. If a baseball were to hit me, ouch, then that baseball, when it hits me, I'm going to feel pain probably, because the energy is being transferred from the moving baseball onto my body, right? And it turns out there are three key things that make this theory work. Number one, that all gases are tiny little spheres. So think of them as tiny little spheres, and they're in motion. Zoom, zoom, zoom. And they're moving in random directions. So one's moving this way and one's moving that way. They're randomly, and when they collide, now there's a fancy scientific term, when they one into the other, they collide elastically. That means there's no energy transferred. Well, actually, that's not true. Elastic means there's no energy lost in the collision. That's basically what that means. So that's the big three tenets of the kinetic idea of motion. And if you think about it, we've got this picture over here. And in this picture, what we've got is the molecules. You can see them kind of whizzing around inside of a box. So even in this room that I'm standing, there are molecules flying everywhere. The gas molecules are flying everywhere. Or you could look at it from this perspective, is they're just zip, 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 and they're constantly randomly in motion. So kinetic molecular theory, right, is that as you increase the temperature, let's think about this. So they're always moving, right? All the molecules are constantly moving. So what do you think? As you increase the temperature, what happens to the kinetic energy? Does it go up or down? Moment. Think. That's right. It goes up. So if you increase the temperature, since the molecules are moving faster, they'll have more energy. More energy means, you have faster molecules. So as you increase the temperature, the average velocity of the particles also goes up, right? This also goes up because what's happening is as you increase the temperature, they're whizzing around faster. And if they go faster, that means that their velocity is faster, okay? So that leads us to an interesting question. What's the difference between a hot day and a cold day? Let's think about this for a moment. So we're in Houston, and Houston, it gets hot here, right? So it's a hot day, like over here in this picture, so to speak, or you're in an ice pack. What's really the difference? You know what the difference between cold air and hot air is that the molecules, the air molecules, are moving faster on a hot day than on a cold day. Turns out air molecules move at about 1,000 miles an hour on an average day. And if it's a hot day, they might be moving at like 1,200 miles per hour. On a cold day, maybe 800 miles per hour. That's fast. And you see, wait, Mr. Bergmann, that sounds crazy. 1,000 miles per hour? These little particles, zoop, 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 moving around? Yes, they're moving that fast. They're moving crazy fast. And even on a cold, cold day, they're still moving super fast. And if you think about wind, what's wind, right? Wind is air molecules moving in a direction. All right, and if you think of hurricanes, we know hurricanes here in Houston. When you get a hurricane, they've got like 100 mile per hour winds, 100, 200 mile per hour winds, the really bad ones. Then all of them are moving randomly. They kind of cancel each other out. But if you get a bunch of them moving in the same direction, or even a small percentage of them, if 10% of them are all moving in the same direction, then you get a 100 mile per hour wind if it's moving at 1,000 miles per hour. And if you get all of them, you can get 1,000 miles per hour. That would be, of course, devastating, right? So, yeah, That's the idea. And if you look at this graph, I think this is an interesting graph as you're looking at it, is that we're looking at the different temperatures. The blue line, you can see, the blue line represents the cold gases, and this is the number of molecules at different temperatures, and the red line is hot temperature. So not all molecules are moving at the same speed or have the same temperature. So some are moving super fast, illustrated with a long line, if you will, and some are moving slow. But at different temperatures, you find in this graph here, you can find how do I say this? A percentage, the vast majority of them are at one particular speed, if you will, or have a certain amount of energy. And so even in the cold air, there's some that are moving fast, but in the hot air, more of them are moving faster or have greater energy. I just tripped over myself. That's pretty cool. And see, as they're moving around, that helps us to understand an interesting concept, and that concept is called pressure. So pressure, and maybe you've heard about this, they talk about the barometric pressure outside. What is pressure? It's called gas pressure. So when we're talking about gas pressure, in this chart here, the pressure is actually when the ball hits the side of the container. Right? When the baseball hits me, ouch, when the baseball hits me, it exerts pressure on me because it hits the side of the container. And though there's not a container in the air, the molecules are hitting things and they are causing pressure. So it's the force exerted by a gas when it collides with the container. Jot that down, that's important. And if you look at an interesting definition, there's a definition of something called a vacuum. Now a vacuum, you find a vacuum in space, right here. This is space or whatever. And a vacuum is what? That is where there is no gases or empty space. So you can have a vacuum when there is nothing present. And if there's gases on the Earth or on Mars or anywhere, then they're going to be exerting pressure because when they move, they're colliding. It could be low pressure if there's not very many gas particles. So that's gas pressure. And on the Earth, if you think about it, there's this column here. There's this huge column of air stacking on top of us that's miles and miles thick, and that's creating pressure on us. And that's important. And the pressure of gas is actually quite high, much higher than you would probably expect. And the pressure we talk about here on the Earth is called the atmospheric pressure. And it's what's exerted by the gases here on the Earth, right? And let's think about this for a moment. If you live, I've talked about this at some other point. I used to live in the mountains. And what do you think? The higher up you go, what happens to the pressure? Now, again, let's think about the Earth. We've got the Earth, and we've got a mountain. Okay, so if you're standing on the mountain versus standing here in Houston at sea level, what do you think the pressure is? Higher versus lower. Remember that there's all this gas on the surface of the Earth pushing down. At the bottom, there's more gas pushing down than on the top. So when you're at a higher elevation, the air pressure is lower. So the higher up you go, what would you say here? You would say the lower the pressure, right? So the lower the pressure. So when I lived in Colorado, I lived at the top of, or not the top technically, but I lived on halfway up Pikes Peak. If you ever visit Colorado, visit Pikes Peak. And when I lived there, we had about 75% of the air that we do in Houston. So 25% less air up there. So in the mountains, you're going to find lower pressure in the mountains than you will at sea level. And in fact, here is a graph that shows you and illustrates this idea, is that you can see what happens to the pressure as you go further and further. Sketch this in your notes. I think that would be an important thing. So to do a quick sketch, you may want to pause the video as you do that. So pressure is also measured. How do we measure pressure? This is an interesting question. How do we measure pressure? We measure it using something called a barometer. All right? And it's a device that measures pressure. Let me cut to a video where I'm going to show you how to make a barometer. So here's another illustration of what the barometer might look like. And you remember I said in the video that we could use water, but water would make a column that would be like 30 feet tall, not very practical. And so we want to use a more dense liquid. So what's often used, not just often, what is typically used is mercury, kind of a dangerous chemical to play around with. But liquid mercury, because it's super dense, like 11 or 12 or something compared to water's 1, you can just make it, about this tall, about a meter tall, and that's all you need. And then you can measure the pressure super well. All right, when we're measuring pressure, we have some units that we use. We're going to say this: 1 atmosphere is equal to, now this one, 760 millimeters of mercury. Because if you have one of those barometers, then it's equal to 760 millimeters. So 1 atmosphere, let's actually back up. 1 atmosphere is the pressure on an average day at sea level. So here in Houston, we typically are very close to sea level, so we're very close to 1 atmosphere. And that's equal to 700, that's how tall. When you physically measure with a ruler a column of mercury on an average day in Galveston, let's say, that's on the coast, by the way, for those who are not from the Houston area, then you're going to get 760 millimeters of mercury. Okay. There's another measurement that is also used, actually we're going to do 3 more, and that is, we sometimes just say 760 torr. Now this is, a torr is the same thing as a millimeter of mercury, but the torr is named after this dude, Mr. Torricelli, who invented the barometer. But it's also equal to 101.32, something called kPa, which stands for kilopascals. And this is a conversion factor that we can use to calculate pressures. So let's say, for example, that I have a pressure of 610 torr, which was very typical, by the way, when I lived in Woodland Park, Colorado, halfway up Pikes Peak. The question I want to ask is, how many atmospheres is this? So you'd say 610 torr, right, over 1 times a fraction. I want to say torr, 2 R's, by the way, in torr. And then I'm going to use this fraction. There's 760 torr in 1 atmosphere. I get my calculator out, right? That's it. I mean, it's one little step conversion. So I take 760 divided by what? I'll take 610 divided by 760. And I get 0.8. Actually, I think it was more like 75%. So maybe 610 was, maybe we're in the 500s typically. But anyways, 0.8 atmospheres, and probably from a significant digits, it's 0.8, something like that, 0.801, significant figure-wise. So, and you can do the other. If you use this, and maybe let's do a kPa one. Let's say that I've got 1,025 torr, and I want to convert to kPa, fraction. Then I'm just going to say 760 torr. Now these are all equal to each other, so I don't have to go to atmospheres. I can just say is equal to 101.32 kPa. Remember, top numbers we multiply, bottom numbers we divide. So I'm going to take 1,025 times 101.32 divided by 760 gives me 136. So now let's talk about solids, liquids, and gases. Well, gases, they're all spread apart and they're moving around, right? So this little image, I think is pretty interesting, is that the gases you see, they're moving around, they're separated out, but in the liquid state, they're kind of rolling over each other. Does that make sense? Because remember, the kinetic-molecular theory states that all molecules are in constant motion, always, always, always moving. Now, wait a second. Yeah, they're always constantly moving, even liquids. So even a liquid that looks like nothing's happening, the molecules are moving, some faster and some slower than each other, all right? So if you think about evaporation, what's happening when you evaporate? What's happening is that some of the fast ones on the top have enough energy to escape. Because remember, not all of the molecules are moving at the same speed. The ones that can break the bonds that hold them together are the ones that are moving faster, so they're the ones that escape. So if you see kind of a, evaporation, that's what's happening on that. All right, so here's kind of a good example. Here we have some molecules, and when something's evaporating, like let's say you've got an enclosed terrarium or something like that, right? I'm talking about that. Maybe you've got a container right here, and you've got some water down here, and you seal it, right? And so it's going to get all steamy here because some of the humidity, right, is evaporating. And as it evaporates, and it's the fast molecules here that can escape, and as they escape, some of them are turning into a gas, but some of them hit each other and turn back into a liquid, like we can see illustrated with our graphic right here, okay? And for liquids, it's really the same diagram that we talked about a little with the gases a little bit ago, is that some of them are moving at a fast speed. If it's cold, right, the blue line, then you've got an average. Some of them are fast, right? If you look right here and above, they're fast. But if it's a hot temperature, it flattens the curve out, and then you've got some that are way up here that are going super fast. So at a certain point, they're going to escape and turn into a liquid. That's how evaporation happens with the fast ones. That's the key thing. And now let's talk about the kinetic molecular theory in terms of solids. This is where it gets kind of weird, right? What happens is that, I'm going to say something weird, is that all solids are all moving. So I've got a marker right here in my hand. And in this marker, which is made of plastic mainly, right? The plastic is moving. Are you, Mr. Bergmann, are you serious? I don't see it moving unless you move it around. But I'm saying that the molecules in here, and what happens with a solid, they're in a very specific arrangement, very ordered structure, oftentimes crystalline structures. And what's happening is they're vibrating back and forth. So as they're vibrating, and the difference between something that's a hot solid and a cold solid is how fast the molecules are vibrating. And you know this morning, let's say that you were cooking eggs for breakfast or something of that sort. As you were cooking your eggs for breakfast, what's happened is that you start with a cold pan, and the molecules are moving slow back and forth and back and forth. And then when it gets hot, when you put the stove on and to cook your eggs, they're moving faster and faster and faster, and that's the difference between a hot pan and a cold pan. Hot pan, you put your hand on, you burn it. Cold pan, you can touch it, you're fine. But the difference between that is that. Now, here's another interesting point, that's super important point, is that you can slow molecules down. Remember, the kinetic molecular theory says that all molecules are moving all the time. Well, there's sort of one exception. If you cool them down and 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 cool them down, you can reach what is called absolute zero. Absolute zero is the coldest temperature where the molecules stop moving. And absolute zero, right, and we've learned this in the Celsius scale earlier in the year, is at 0 Kelvin, which is minus 273 degrees Celsius. So if you're 273 degrees below zero, these molecules are not vibrating anymore. They have stuck together, and they are stopped. So that's absolute zero. So the key thing to take away from this video is that in the kinetic molecular theory, all molecules are constantly moving, right? And gases are, flying around. Liquids are kind of rolling over each other. Solids are vibrating. And you can get them so cold that they'll stop moving. By the way, it has to be a solid when that happens, because as things cool, in our next video we're going to talk about that, as things cool, the gas turns into a liquid, and then if it cools further, the liquid turns into the solid, and if you keep cooling and cooling, you can stop it and get only when you get, say, to absolute zero. Hey, Houston, we don't have a problem. We'll see you in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.